Okay, so in the last video we learned that we can calculate work as a line integral if F is a force field and I've got a particle moving along a piecewise smooth curve C. We simply integrate F dotted with T, where T is our unit tangent vector, with respect to arc length. Okay. And we can remember where this comes from. This is essentially my displacement vector. The unit tangent vector approximates the direction of the curve, and I'm scaling it by the arc length of a little piece of that curve. Okay, now, of course, we learned how to evaluate line integrals. I would take that curve and I would parameterize it. So I would have r of t as t varied from a to b. And of course, if it was piecewise smooth, I just have multiple functions, one for each piece. So I know that this would become the integral from a to b. And then what I need to do is express my integrand, which is f dotted with t, in terms of t, in terms of my parameter here. Initially, everything would be expressed in terms of x and y, or x, y, and z if we're in 3 space. But if f is being evaluated at a point, I'm just going to describe that point as r of t. So f becomes f of r of t. That's fairly familiar that we use composition to switch from expressing our function in terms of this set of variables to that set of variables. And then t, well, that's just the unit tangent vector. So that's just r prime of t normalized. And then I know if I'm switching from ds to dt, I'm always going to have a scaling factor. Anytime I change the differential at the end of my integral, there's some scaling factor to account for the fact that ds is not the same as dt. Okay, small change in arc length, not necessarily equal to a small change in time. That makes sense. All right, my scaling factor I know is the magnitude of r prime of t, and check out how nice that is. That magnitude cancels, and so work becomes the integral from a to b of f of r of t dotted with r prime of t dt. Now, as we'll see in one of the later videos, there's a lot of different notation that you can use for a work integral. And I will show you all of the different types of notation that show up in our textbook. Okay. But what you see on the board right now are my 2 favorites. I really like this because it reminds me of where it came from and what it means. Force dotted with displacement. Displacement's a vector that has a magnitude and a direction, and I can see all of those pieces in the integral. This tells me exactly what I need to do to evaluate a work integral. So this is going to be incredibly helpful as we work through our first example. So let's suppose we've got a force field in 2 space. Let's suppose it's x, x, y. Okay. And let's suppose that C is the top half of the circle of radius 2, oriented counterclockwise, CCW for counterclockwise. Now, I mentioned in an earlier video that orientation didn't make a difference for line integrals. It does for work integrals. And you might think that's a contradiction. It's not, and we'll discuss why. Okay? But if you just think about it with common sense, me biking into the wind, very different experience from me biking with the wind to my back. So the orientation absolutely makes a difference about whether the force is helping or hurting the particle. For a general line integral, changing the orientation doesn't change things. But for a work integral, that unit tangent vector encodes the direction of the curve. So changing the orientation changes part of the integrand, and therefore it does affect things for work integrals. Okay, excellent. So if I have this, I'm going to go ahead and parameterize my circle. I think I'm going to go with r of t equals 2 cosine t, 2 sine t, 0 less than or equal to t, less than or equal to pi, because I only want the top half of that circle. Okay. That means r prime of t is going to equal negative 2 sine t, 2 cosine t. Okay, excellent. I'm going to just copy down over here that my force field F of xy was x, xy. That way I can erase the left side of the board here so that we can work through this. Suppose I might have wanted to keep up this, that we're going to get the integral from a to b of f of r of t dotted with r prime of t dt. Okay, so we'll have the integral from 0 to pi. I need to take f, but I need to write it in terms of r of t. So notice, with r of t, that's just telling me that x is 2 cosine t, and y is 2 sine t. So my first component function x is just 2 cosine t. The second component function is xy, and that's just going to be 4 sine t cosine t. We're going to dot that with r prime, which is negative 2 sine t, 2 cosine t, and then we're integrating that with respect to t. Excellent. Now, before I integrate, I got to do the dot product, okay? We are using vectors to create this real valued function that we're integrating, but a line integral is about integrating a real valued function, not vectors. Okay? So I work out that dot product. So I'm going to get negative 4 cosine t sine t plus 8 cosine squared t sine t dt. I'm just going to split that into two integrals. Integral 0 to pi, and I'm going to pull out the constants, negative 4 cosine t sine t dt plus 8 integral from 0 to pi cosine squared t sine t dt. And for both of these, it looks like I can do the same u sub. Let's just let u equal cosine of t. If I were just doing this one, I'd probably choose u equals sine t. But since I've got to do a u sub with u equals cosine t here, might as well do the same one for both. So now du is negative sine t dt. So over here, that negative with the sine t and the dt will all become the du. So this is going to become 4. Integral from the u value at 0 is cosine of 0, which is 1, to the u value at pi is cosine of pi, which is negative 1, and then we're integrating u du. Plus 8 copies of, those limits of integration change to exactly the same values, negative 1 and 1, but with the negative 1 on top, u squared du. Okay. Let me clear some space. So, coming over here, I'm going to get 4 copies of u squared over 2 evaluated between negative 1 and 1, plus 8 copies of u cubed over 3 evaluated between negative 1 and 1. So, that's going to be 4 halves, which is 2. That's going to be 2 copies of, let's see, 1 minus 1, plus 8 copies of, I'm going to get negative 1/3 minus 1/3. So I'm getting 0 plus 8 times a negative 2/3, which is going to give me a negative 16/3. Is it okay that I got a negative answer? Absolutely. What that tells us is that this particular force field is spending a lot more energy trying to push the particle back than it is trying to give the particle a helping hand and move it along.